fifth problem, that is priority scheduling.
What will
Priority
mark?
scheduling is a CPU scheduling method used in operating system when many processes are waiting to run. The OS chooses the process with the highest priority first. Lower number is equals to higher priority. The main goals are better CPU usage, less waiting time, fair execution of process. It is used in real time and general purpose systems. Low priority process may never get CPU time if high priority processes keep coming. This is called starvation. The OS uses aging, which slowly increases the priority of processes. The OS uses aging, which slowly increases the priority of processes waiting for a long time. This ensures fairness, so every process eventually gets CPU time. Next is experimental setup. This section explains the system used to implement and test priority scheduling algorithm with aging. Hardware setup. We used a basic computer with an Intel quad-core processor, RAM between 4 to 8 GB, operating system like Windows, Linux, Mac OS, compilers such as GCC, MeanGW, and Clang, code editor like VS Code, Code Blocks, or Terminal. And the software tools are: the program is written in C language, compiled using GCC, MeanGM, and Clang. Editing was done in VS Code. Extension used C extension and Code Runner optional. And the next one is input parameters. Each process in our scheduling program has a PID, unique ID of the process. Arrival time, when the process enters the ready queue. Burst time, how much CPU time it needs. Priority, lower value means higher priority. And the next one is output parameters. After running the algorithm, the program gives complete time, turnaround time, waiting time, average waiting and turnaround time, starvation behavior before and after applying aging. And the next one is a data set used. We tested the algorithm with three data sets, that is data set A, data set B, data set C. Here data set A, small 3 processes, and data set B, 5 processes, data set C, 5 processes. Data set A is simple scheduling, data set B is different arrival, burst, and priority values. Data set C is designed to show starvation in normal priority scheduling. And next, implementation steps. This section explains how the scheduling system was built step by step. First step, define process structure. We first create a structure to store all details of a process. Each process has PID, arrival time, burst time, remaining time, priority, waiting time, turnaround time, and completion status. And the second step is select scheduling type. We use primitive priority scheduling because it immediately responds to new high priority process. It works like real operating systems, and aging works better with primitive. And the third one is implementation aging. Aging is applied so that long waiting processes don't starve. We increase the priority of every waiting process by one. After each time unit, smaller number is equals to higher priority. And the step 4 is execution cycle. The CPU executes step by step, and the first one is increase time, second one is check which processes have arrived. Next, select the highest priority process, execute it for one time unit, applying aging to waiting processes. And the last is mark a process completed. When it finishes, repeat until all processes are completed. And the fifth step is generate output values. For each processes we calculate turnaround time and waiting time. Finally we store and display the results in a table. And the observation without aging, processes with low priority waiting executionally in data sets where many high priority processes exist, starvation occurred. Waiting time become very large for low priority processes. With aging, all processes eventually executed. Waiting times were more balanced and no starvation observed. Even in starvation prone data set, average TAT and waiting time improved for all low priority processes, slightly overhead due to frequent priority updates but negligible. Behavior of primitive scheduling, higher responsibility, frequent contestant switches, shorter task benefit more. And the last one is comparative execution. Here, to compare the algorithm with and without aging, the same data set was used. Process set example, we take a data set PID of P1, P2, P3 with respect to the arrival time 0 to 4 and the burst time 532 and initial priority 3, 4, 5 respectively. Results without aging, PID process P1, P2, P3 burst time 532 respect to the waiting time 036 with respect to the TAT 568. Analysis without aging, P3 has a high waiting time due to continuous arrival of equal or higher priority task. Lower priority processes wait longer. Starvation may occur in behavior datasets, and the results with aging is the PID P1, P2, P3 with respect to the burst time 532, waiting time 321 and the TAT 853. Analysis with aging, all waiting times reduced significantly. P3 gets CPU earlier due to priority boost. System becomes fair and balanced. Aging prevents starvation and effectivity. Here the code, this program performs primitive priority scheduling with aging. Input stage, the user enters arrival time, burst time and priority for each process. Each process stores this value along the remaining time, waiting time, turnaround time, etc. Scheduling loop, the CPU time starts from t equal to 0 and runs until all processes finishes. At every time until at every time find the process with the highest priority. Lowest priority number is equals to highest priority. If no process has arrived, increase time. The highest priority process executes for time one time unit. Primitive aging is applied, all waiting processes get their priority improved, decreased. If a process finished, mark it completed, calculate turnaround time and calculate waiting time. And the next one is output stage. Here the output is, and this table shows the final result of the primitive priority scheduling with aging. The CPU scheduling process based on priority, lower number is equal to higher priority. Aging increased the priority of waiting processes, so no process was starving. For each process, the program calculated waiting time, how long the process waited, the ready queue, turnaround time, total time from arrival to completed. Example, process 1 waited 5 units and finished in 8 units. Process 4 had the shortest waiting and finishing time because it arrived earlier with good priority. And the last one is conclusion. Here the conclusion, the implementation of priority scheduling with aging successfully removes the problem of starvation, found in basic priority scheduling. By gradually increasing the priority of waiting processes, the scheduling ensures fairness and allows all processes to complete in reasonable time. The result show improved waiting and turnaround times, especially for low priority tasks, making the aging enhanced algorithm more balanced, efficient, and suitable for real time operating systems.